This is the third lecture in the climb performance. In this lecture, we will discuss the altitude effect towards the climb angle and the climb rate. Before we see the altitude effect, let's do a bit summary about what we've learned about the climb angle and the climb rate. And first of all, we know the climb angle gamma is calculated through arcsine T minus D divided by W. Basically, it's about the excess thrust. And so in the climb angle, we have the best climb angle speed, Vx. So when the aircraft is climbing at this Vx speed, and it can achieve the largest climb angle. And also we have the climb rate. Basically, it's vertical speed, Vc. So it's excessive power. And also we have the best climb rate speed, Vy. And when the aircraft is climbing at speed Vy, and it can have the largest vertical velocity Vc, or the best climb rate, maximum climb rate. And normally Vy is larger than Vx. Okay, and in the meantime, we also have when we discuss the climb angle, we discuss the minimum drag speed, VMD, and VMD is normally larger than Vx. And there's one important case we need to remember. So VMD, minimum drag speed, equals the best climb angle speed, VMD, equals Vx, only when the thrust is assumed to be constant. For when we discuss the climb rate, we introduce the minimum power speed, VMP. So normally VMP is smaller than Vy. So this is a summary of what we've learned in the previous two lectures. Now we are going to answer how gamma and Vc vary with increasing altitude h. Okay, so first of all, we assume the aircraft climbs at constant airspeed. And we know the height or the altitude increases, the density, air density decreases, and the thrust will also decrease. This is because, for example, for the jet engine, the mass of the air ejected reduces, and therefore the reaction, that's the thrust, reduces on the aircraft. And we should notice this T is not temperature but thrust in here. Okay, and similarly, the increasing altitude density decreases, and the parasitic drag reduces. And this is because dp, parasitic drag, is calculated as half rho v squared times s times cdp. And we can notice cdp has a dot on top of it, above it. So the coefficient, drag coefficient, parasitic drag coefficient is a constant. V doesn't change, S doesn't change because the density changes, so dp is reduced. And let's walk further for the other component, di, the induced drag. And we assume climb at a small angle, so lift can be approximated by W, and then W is half rho v squared times S times CL. And because the density is reduced and V and S are the constants, and also the mass doesn't change, so CL will increase. In this case, because CDI is proportional to CL square, so the CDI increases in a higher rate. So we have two arrows in here to indicate faster growth. So DI growth increases faster than CL. Okay, So finally, the total drag will increase overall because dp is a first order decrease, but CDI is increases faster. We have two arrows here as indication. So the total drag increases in all overall. Then the climb angle gamma will decrease because the thrust decreases and the total drag will increase. So overall, gamma will decrease. And it's the same for the climb rate. We see it will also decrease with a growing altitude. In the previous slide, we know both gamma and VC, the climb angle and the climb rate, will um, decrease with increasing altitude. Now, let's introduce two other concepts, the absolute ceiling and the surface ceiling. And in practice, we know Vx and Vy, they will also change with altitude. And Vx, which is the best angle of climb speed, will increase with increasing altitude. And in a country, the best rate of climb speed, Vy, will decrease. So they will converge. Vx and Vy will converge to one point at a certain height. And the example shown here is converges to about 19,000 feet. So that conversion point, we name it as absolute ceiling. So the absolute ceiling of an aircraft is defined by the converging Vx and Vy. So at this point, the thrust is only able to combat the drag, and there is no excess power to further increase for the aircraft to increase its altitude. So that's why we call it absolute ceiling. And for real flights, we also certify the surface ceiling. So at surface ceiling, the aircraft is unable to climb at a rate greater than 100 feet per minute. That's equivalent to about 0.505 meter per second. So with all engine operative, so the surface ceiling is slightly lower than the absolute ceiling. So to give some margin for the aircraft in a safety, especially safety margin. Most jetliners have a certified surface ceiling of about 42,000 feet. And some business jet has surface ceiling even higher to about 50,000 feet. And the Concorde supersonic jetliner has even higher surface ceiling, about 60,000 feet.